Wake up! Are you ready to learn about properties? The purpose of today's video is for you to be able to identify and use properties to add and subtract rational numbers. And I'm going to be using the Frayer model to demonstrate each of these properties. The first property we're going to talk about is the identity property. I've provided examples of the identity property in this lower left-hand corner box. What I'd like you to do next is to pause the video and come up with characteristics that these examples have in common. And you're going to fill in your characteristics in this upper right-hand corner box. Then you're going to unpause the video and compare your characteristics to what I came up with. Go ahead and give that a try. All right, two characteristics that I said they had in common is that when adding 0 to a number, it does not change the number. So right here we have a 5, we added a 0, it's still a 5. We have a 3, we added a 0, it's still a 3. We use a variable, we add 0, and it's still the same variable j. And then when multiplying by 1, it also does not change the number. For example, 8 times 1 is still 8, and 1 times x is still x. So those are some characteristics I noticed about these examples. So I put that in this box. Now I'm going to try to come up with the definition of the identity property in my own words. So once again, pause the video, and then in this upper left-hand corner box, try to describe in your own words what you think the identity property is. So the definition I came up with is that when you add 0 to a number, or you multiply a number by 1, the number stays the same. It keeps its identity. Now let's come up with some non-examples of the identity property. And I'm going to use some of these where students sometimes make a mistake. So 5 plus 1 is 6. Some students might look at this non-example and think this is the identity property because of this 1. But I started with a 5. Did I end up with a 5? Did the 5 keep its identity? No. It's only when you multiply by 1 where that would be the identity property. Another example, -4 plus 4 equals 0. Some students might look at this and see the 0 because they remember that the identity property has something to do with a 0. But I started with a -4. Did I end up with a -4? No. These are actually called opposites or additive inverse. We talked about that in a previous video. Another non-example would be 7 divided by 0. Once again, you might see the 0 and think, oh, it's the identity property. But I don't end up with what I started off with. This is actually not even possible in math. It's undefined. Because remember we talked about 7, I cannot break up into groups of 0. At least one group would exist. So this is not even possible. All right, let's go on to the next property. Our next property is called the commutative property of addition. And I've provided examples, once again, of this property. So go ahead, pause the video, and up in the upper right-hand corner box, write any characteristics that you see that each one of these have in common. The characteristics that I saw that they each had in common is that the numbers changed location or traveled in each problem. So for example, the 1 and the 4, they switched places. The 5 and the 7. The 5 is first, the 7 is second, but in this side of the problem, the 7 is first, the 5 is second. So in all of these, the numbers are changing location or traveling. Addition was used in each problem, and the answer is the same on both sides of the equal sign. And what I mean by that is that the sum of 1 and 4 is 5, and the sum of 4 and 1 is 5. The sum of 5 and 7 is 12. The sum of 7 and 5 is 12. So the sum is the same on each side of this equal sign. And how I remember this property is I think of the word commute. What does that mean? Some of your parents might commute to work every day. They travel or they change location. So I always remember this property is that the numbers are changing location, but we still end up with the same sum. Go ahead, now pause the video again and try to come up with the definition of the commutative property of addition in your own words. What I came up with is numbers that can be added together in any order and you would still get the same sum or answer. And the key word here is added, because I'm going to show you a non-example. A non-example would be 4 minus 1 and 1 minus 4. Although the two numbers change location or switched, I do not get the same answer on both sides of the equal sign. This is 3. However, 1 minus 4 is negative 3. Those are not equal. And remember, you have to have the same answer on both sides of our equal sign. So that would be a non-example. Another non-example would be 2 plus 3 equals 3 plus 7. Yes, the 3 did change location. It started as the second term, and on this side it's the first term. However, we don't have the same constants on both sides of the equal sign. Over here we have a 2, and on the right-hand side we have a 7. And another reason it would be a non-example is that 5 does not equal 10. And remember, it has to be the same answer on both sides of the equal sign. Okay, let's move on to our next property. This property is called the commutative property of multiplication. It's very similar to the commutative property of addition. However, we're just working with multiplication. So go ahead and look over those examples and fill in some characteristics in the top upper right-hand corner box. So once again, the numbers changed location or traveled. For example, 2 times 6, the 2 is first, the second number is the 6. However, on this side, it's 6 times 2, so the numbers just switched spots. Or 4 times 3 and 3 times 4. Notice the parentheses are still in the same location. What changed or traveled locations are the numbers. They switched places. Multiplication was used in each problem. I used specifically the dot in this problem versus the parentheses in this problem so that you know in math, anytime you see this symbol, it means multiplication. And anytime a number is right next to parentheses, that also means multiplication. And then finally, the answer was the same on both sides of the equal sign, or the product. In math, we use the word product as an answer to our multiplication equations. So 2 times 6 is 12, and 6 times 2 is 12. We have the same product on both sides. 4 times 3 is 12, and 3 times 4 is 12. So no matter what, whatever order we multiply numbers in, we're always going to get the same product. Go ahead and come up with your own definition now of the commutative property of multiplication. The definition I came up with was numbers that can be multiplied in any order, and the product would be exactly the same on both sides of the equal sign. So let's talk about some non-examples. One example would be 8 divided by 2 equals 2 divided by 8. Does this problem have multiplication in it? No. So that's one reason it doesn't represent this property. But the reason that this property doesn't work with division is, what is 8 divided by 2? It's 4. What's 2 divided by 8? Well, if I were to simplify that, that's 1/4. So that's the same thing as 25 hundredths. Those are not equal. So it's not the commutative property of multiplication because it's not the same answer on both sides of the equal sign. Another non-example would be 4 times 3 equals 3 times 5. Although the 3 changed location, we don't have the same constants on both sides of the equal sign. Over here we have a product of 12, and over here we have a product of 15. Those are not the same. Our next property is the associative property of addition. Look over these examples and let's see some characteristics that they have in common. The first is that the numbers are in the same order. And what I mean by that is that on this side, let me get my pen real quick. On this side of the equal sign, notice the order is 4, 9, 3. On this side of the equal sign, it is still 4, 9, and 3. So the numbers didn't travel or change location. That's why it's not the commutative property of addition. Once again down here, 3, 6, 1. 3, 6, 1. The numbers are in the same order. The next characteristic is that it's the parentheses that are moving. So let me go ahead and erase these lines so you can see the parentheses. Notice in this first example, the parentheses are around the first two numbers, where on this side of the equal sign, the parentheses are around the second two numbers. So it's the parentheses that moved. Same with this example. The parentheses started here, and they ended up in the back on this side. Addition was used in every example. And finally, the sum, that's the answer to an addition problem, is the same on both sides of the equal sign. So if I were to solve this, 9 plus 4 is 13, and 13 plus 3 is 16. Let's see if that's the same on this side. In order of operations, you always do grouping symbols first. So we would have to do the 9 plus 3 first, which is 12, and then 4 plus 12, which is also 16. I'll prove that on this one as well. 3 plus 6 is 9, and 9 plus 1 is 10. Let's see if this side equals 10. Grouping symbols first. 6 plus 1 is 7, plus 3 is also 10. So both sides of the equal sign has a sum of 10. Go ahead and pause the video now and see if you can come up with your own definition for the associative property of addition. My definition was that when moving the grouping symbol, or parentheses, in an addition problem, the sum or the answer will not change. Did you have something close to that? Good. All right, let's provide some non-examples. So the first non-example I'm going to provide is 2 minus 4, let's put those in grouping symbols, parentheses, minus 5 equals 2 minus 4 minus 5. The reason this is not the associative property of addition is, one, because it's all subtraction. But let me show you why subtraction doesn't work in this property. In grouping symbols first, we would solve 2 minus 4, which is a negative 2. And if I took 5 away from a negative 2, I would end up with negative 7. On this side of the equal sign, I would need to do parentheses first. 4 minus 5 is negative 1. 2 minus a negative 1. When you see a double negative next to each other, what that means is, what is the opposite of a negative? It's a positive. So that would be 3. Does negative 7 equal 3? No. That's why subtraction will not work with this property. Here's another non-example. that sometimes confuses students. 4 plus 9 in parentheses plus 3 equals 9 plus 4 in parentheses plus 3. Notice our numbers have to be in the exact same order on both sides of the equal sign. So 4, 9, 3. On this side, does it say 4, 9, 3? No. This is actually an example of the commutative property because what happened is the 4 and the 9 traveled or changed location or commutative property. The grouping symbols didn't move. The group is still around the 4 and the 9 and the 9 and the 4. The same two numbers are in the grouping symbols. So that's why it's not an example of the associative property. Let's move on to our next property. This is the associative property of multiplication. Very similar to the associative property of addition, but we're just using multiplication. So some characteristics that these examples have in common is that the numbers are in the same order. Once again, we have 2, 5, 3, 2, 5, 3. The numbers do not commute or change location. That's why it's not the commutative property of multiplication. What's moving or changing is the grouping symbols. So the 2 and the 5 are in the parentheses on this side, where over here, the 5 and the 3 are in the grouping symbols. 8, 4, 2, 8, 4, 2. The numbers do not change location. It's the groups that are changing. The parentheses are moving. Multiplication is used in every problem, and the product is the same on both sides. So 2 times 5 is 10, times 3 is 30, and on this side, remember, always do grouping symbols first. 5 times 3 is 15, times 2 is also 30. We have the same product on both sides. Go ahead and come up with your own definition. So what I came up with is that when moving the grouping symbol or parentheses in a multiplication problem, the product or answer will not change. So let's go over some non-examples. Why doesn't division work for this property? Well, let me show you. 8 divided by 2, we're going to put that in parentheses, divided by 2 equals 8 divided by 2 divided by 2. Notice the numbers are in the same order. 8, 2, 2, 8, 2, 2. What's moving are the grouping symbols, the parentheses. And in math, order of operations, we always do our grouping symbols first. So 8 divided by 2 is 4, divided by 2 is 2. But on this side of the equal sign, we have to do the grouping symbols first. 2 divided by 2 is 1, and 8 divided by 1 is 8. 2 does not equal 8. So that would be a non-example. Another non-example would be 5 times 3 times 1 equals 3 times 5 times 1. Notice our numbers are not in the same order. 5, 3, 1, 3, 5, 1. What happened here is that the 5 and the 3 changed location. So yes, we do have the same answer on both sides of the equal sign or the same product. This would be 15 equals 15, but it's not associative property because the grouping symbols did not move. The grouping symbols are still around the 5 and the 3 on both sides. What moved was the order of the numbers, and that's commutative property of multiplication. This property should look very familiar to you because we just had a video on this. Remember the additive inverse? Here are some examples, and remember the characteristics of additive inverse is that our answer is always 0. And also, anytime we add opposite numbers, we always have an answer of 0 or a sum of 0. Remember, opposites are the same distance from 0 on the number line, but in opposite directions. So -1 and 1, 4 and -4. So the definition I came up with was that when adding opposites, you will always get a sum or answer of 0. Let's provide some non-examples. Why does multiplication not work for additive inverse? 3 times -3. Those are opposites. However, the answer is not 0, it's -9. So that would not be additive inverse. Or let's try division. 8 divided by -8. Those are opposites, but the answer, or the quotient, remember we use quotient in math for the answer to a division problem, would be -1, not 0. All right, our last property. You're probably thinking, so am I. This last property is the multiplicative inverse. I saved the most difficult for last. Go ahead and look over these examples. Let's talk about some characteristics they have in common. Each answer is 1. Multiplication was used in every problem. They all had rational numbers, numbers that can be changed into fractions. And the reason that the answer is always 1 is because we multiplied by the reciprocal in each problem. This first example, 5/2 times 2/5, you can easily see the reciprocals here. Remember, a reciprocal is when you flip the fraction. The reason the answer will always be 1 is because you can cross simplify, or you might know that as cross divide, the 5's. 5 divided by 5 is 1. And we could cross simplify or cross divide the 2's. 2 divided by 2 is also 1. So you end up with 1 times 1, which is 1. Or this next example, 3. 3 I can write as a rational number, 3/1, times its reciprocal, 1/3. Cross simplify the 3's, and I get 1. The next one's a little bit trickier. 8/10. Well, 8/10 I can simplify by dividing by 2, which is 4/5, and the reciprocal of 4/5 is 5/4. Cross simplify, and I end up with 1. And this last example, 4 1/2. I can change that to the improper fraction 9/2. And how did I get that? 2 times 4, 8, plus 1, 9. Its reciprocal is 2/9. Cross simplify the 2's, cross simplify the 9's, and you get 1. So we always had a product of 1. Go ahead and come up with your own definition. The definition I came up with, when you multiply a number by its reciprocal, you will always get 1. All right, finally, let's talk about some non-examples. Why does addition not work for this property? Well, if I had the reciprocals 1/2 and 2/1, when adding fractions, you have to have a common denominator. So the common denominator would be 2. So I'd change this to 1/2 plus 4/2, which is 5/2. Right now it's an improper fraction. If I were to change that to a mixed number, 2 goes into 5 twice, which is 4, so there would be 1 left over. 2.5 is not the same thing as 1. Remember, the product has to be 1 for this property. Another non-example would be 3/4 times 3/4. Well, I do not have reciprocals right here, so that's one reason it wouldn't work. And I also won't get the product of 1, because 3 times 3 is 9, and 4 times 4 is 16. That's not 1. Let's see why division wouldn't work. If I had the reciprocals 8 over 2 divided by 2 over 8, I could first simplify these fractions to 4 over 1 divided by 1 over 4. Remember, when dividing fractions, you actually multiply by the reciprocal of the second fraction. So the reciprocal of the second fraction would be 4 over 1, so my answer would be 16 and not 1. Phew, 7 properties. That was a lot. Because there were so many properties, you might want to go back and rewatch the properties you still have questions about at another time. Thank you for watching the video, and we'll see you in class.